everyone. In the previous video, we discussed about what is a complex function and how we can find the real part and the imaginary part of a complex function. Okay, first of all, we define the complex function. Then next, moving to what is the limit, continuity and derivative of a complex function. Okay, as we studied in calculus, if a function is defined, then we are moving to the next topics: limits, continuity, derivative, integration, etc. So as in the real valued functions, here also we can find the limit and we can check the continuity and what about the derivative of a complex function. Okay, first of all, limits. A function f of s is said to have the limit capital L as z approaches to z0 is written as limit z tending to z0 f of z equal to L. Here our complex function is f of z and the limit value is capital L. So it can be written as limit z tending to z0 f of z equal to L, which means as z approaches to a particular point z0, a function f of z will approaches to a value capital L. That is, for every positive real number epsilon, we can find a positive real delta such that for all z not equal to z0 in the disk mod z minus z0 less than delta, we have mod f of z minus L is less than epsilon. This is a formal definition of limit. That is, for every positive value epsilon, we can find a delta positive such that as mod z minus z0 less than delta, we have mod f of z minus L, which is less than epsilon, which means as z approaches to z0, then f of z tends to capital L. Here, in the real case, x approaches to x0 only along the real line. Okay, in real cases, we discuss about the x approaches to x0 only through the real path. But here, in the case of complex function, here z approaches to z0 from any direction in the complex space. It may be through x-axis or through y-axis or through a curve or a line, etc. So here we want to check along each paths, real path, imaginary path, or through a line or a curve, etc. And if a limit exists, it is unique. Along each path we get a limit. We said that the limit exists if it is unique. Next, we are moving to continuity. What is continuity? A function f of z is said to be continuous at a particular point z equal to z0 if f of z0 is defined and limit z tending to z0 f of z equal to f of z0, which means the limit at the point z tending to z0 exists and it must be equal to the functional value at z0. Then we said that the f of z is continuous at z equal to z0. These are the properties. That is, if f and g are two complex functions which are defined and continuous at z equal to z0, then we have f plus g is continuous, f minus g is continuous, f into g is continuous, some scalar into function is continuous, and f by g is continuous provided the denominator part, that is g, is defined. So these are the properties for continuity. Next, we are moving to some problems. Check whether f of z is continuous at z equal to 0 if f of 0 equal to 0. It is defined that f of 0 equal to 0. So we are moving to the first problem. First problem is real part of z divided by 1 minus mod z. We are going to check this function is continuous at z equal to 0. First of all, I am writing it in the limit form. That is limit z tending to 0, real part of z divided by 1 minus mod z, that is equal to limit. We know that z equal to x plus iy. So z approaches to 0 means the coordinate xy approaches to 0, 0. Then numerator is real part of z, which means x, divided by 1 minus mod z. When z equal to x plus iy, then mod z equal to root of x square plus y square. So here x divided by 1 minus root of x square plus y square. This is the function. Next, I am going to check the limit along the x-axis. Along the x-axis means at the y coordinate is 0. Therefore, the above expression becomes limit xy tending to 0, 0, x divided by 1 minus root of x square plus y square equal to limit x tending to 0, x divided by 1 minus root of x square, because we are checking it along the x-axis, so y equal to 0. Then next, give x tending to 0. So the value becomes 0 divided by 1, which is equal to 0. So along x-axis, I am getting the limit as 0. Next, I am checking along this limit through y-axis. Y-axis means which is the imaginary axis, so the real part is 0. So x equal to 0. Then limit xy tending to 0, 0, x divided by 1 minus root of x square plus y square is equal to, put x equal to 0. So we get limit y tending to 0, 0 divided by 1 minus root of y square. Then y tending to 0 implies the limit is 0 by 1, which is equal to 0. Next, I am checking the limit along a line segment. Here I am taking the line y equal to mx, where m is the slope of this curve. Let's see what about the limit. So limit xy tending to 0, 0, x divided by 1 minus root of x square plus y square is equal to limit, put y equal to mx. So numerator is x divided by 1 minus root of x square plus, instead of y, mx the whole square. So here the function depends only on the variable x. So limit x tending to 0. Then limit x tending to 0, x divided by, in the denominator part, 1 minus root of x square plus m square x square. So x square is a common term, that is 1 minus x into root of 1 plus m square. Next, give the limit x tending to 0. So the numerator becomes 0. So the limit is 0. So along y equal to mx, we get the limit 0. And along the x-axis and along the y-axis, we get the limit as 0. So both in 3 cases, we got the limit as 0. Then we conclude that along all these paths, the limit is 0. And also given that f of 0 equal to 0. So here limit z tending to z0, f of z equal to f of z0, which is a condition for continuity. Therefore, limit z tending to z0, real part of z divided by 1 minus mod z equal to 0, which is equal to f of 0. Therefore, our function is continuous at z equal to 0. Next problem. Check this function is continuous at z equal to 0. That is imaginary part of z square divided by mod z square. First of all, find what is z square. Z square is x plus iy the whole square, that is equal to x square minus y square plus I into 2xy. Here the function is imaginary part of z square divided by mod z square. So our function will be limit xy tending to 0, 0 to xy divided by x square plus y square. Here also we are checking the limit through x-axis, y-axis and through a line. First case along the x-axis. So here y equal to 0. Therefore the function will be limit x tending to 0. The numerator is 0 divided by x square plus 0, which is equal to 0. Along y-axis, which means x equal to 0. So the limit will be limit y tending to 0, 0 divided by 0 plus y square. So the answer is 0. So along the x-axis and along the y-axis we get the limit as 0. Next case, along y equal to mx. Our function is 2xy divided by x square plus y square. Put y equal to mx. We get limit x tending to 0, 2x into mx divided by x square plus mx the whole square. Upon simplification, we get limit x tending to 0, 2m x square divided by x square plus m square into x square. Taking x square as a common term, then limit x tending to 0, 2m divided by 1 plus m square, which is equal to 2m divided by 1 plus m square. What is m? Here we are taking the line y equal to mx. So m is the slope of the line, which depends on line segment. So here the limit depends the value of m. If m varies, the limit varies. Therefore, the limit depends on value of m, which is a slope, varies depending on the line. So it is not unique. When along the x-axis we got the limit as 0, along y-axis we got the limit as 0, but along y equal to mx we didn't get a unique limit. Therefore, the function is not continuous at z equal to 0. Next, moving to derivatives. A derivative of a complex function f at a point z0 is written as f dash of z0 and is defined by, this is the formal definition, f dash of z0 equal to limit delta z tending to 0, f of z0 plus delta z minus f of z0 divided by delta z, provided the limit exists. This is the formal definition of derivative. If delta z equal to z minus z0, that is change in the complex variable, then z equal to z0 plus delta z. Then we can rewrite the above definition as f dash of z0 equal to limit z tending to z0 f of z minus f of z0 divided by z minus z0. Also, if f of z is differentiable at z0, then it is continuous at z0. Differentiability implies continuity at the same point. Next, moving to the rules. If f and g are two differentiable functions, then we have these properties, that is c f derivative. Derivative of c into f, where c is a constant, is equal to c into derivative of f. Then derivative of f plus g equal to f dash plus g dash. Derivative of f into g equal to f g dash plus f dash g, which is the product rule. And f by g dash is equal to g f dash minus f g dash divided by g square, which is the quotient rule. These are the basic properties of derivative, already studied in the real valued functions. Next, moving to the problems. Find the value of the derivative. Here the function is z minus I divided by z plus I at the point I. Here the function is of the form rational. It is a rational form function. So derivative of z minus I divided by z plus I, we use the quotient rule. Quotient rule means denominator into derivative of the numerator minus numerator into derivative of the denominator divided by denominator the whole square. So here f dash of z equal to z plus I into 1 minus z minus I into 1 divided by z plus I the whole square, that is equal to, upon simplification we get 2I divided by z plus I the whole square. This is the derivative of f. Next, we are finding what about at z equal to I. So put z equal to I, we get f dash of z equal to 2i divided by I plus I the whole square, that is equal to 1 by 2i. So the value of derivative of the function z minus I divided by z plus I at the point z equal to I is 1 by 2i. Next problem, the function is I into 1 minus z whole power n at z equal to 0. So here f dash of z equal to, what is the derivative of z raised to n with respect to z? N into z raised to n minus 1. So here we get I is a constant, 1 minus z whole power n means n into 1 minus z power n minus 1. Here we are differentiating with respect to z. So the coefficient of z is minus 1. So 1 minus z into whole raised to n minus 1 into minus 1. At the point z equal to 0, we get the answer as minus ni. Next problem, function is z minus 4i whole power 8 at the point z equal to 3 plus 4i. Here also the derivative is 8 into z minus 4i whole power 7 and put z equal to 3 plus 4i, and on simplification we get the value as 17496. So these are the concepts of limit, continuity and differentiability of the complex function.